Hi, in this video we're going to be looking at our tutorial 5 question 3 on pipeline hazards. Okay, so this is the code that we are given, and executing this code on a normal single cycle processor is not going to cause any issue because uh, for a single cycle processor we execute each instruction one by one and we complete each instruction before going on to the next instruction. Okay, but in a pipeline processor we have seen that multiple instructions will occupy the different stages of the processor at the same time. Okay, and that can introduce problems both in terms of data and control. Okay, so that leads us to figuring out how we can handle these data hazards as well as control hazards. Okay, so if I look at just a quick analysis of this code, you can see that in the first instruction we are updating register T1, and T1 is actually needed as a source register in instruction 2. Okay, but we know that this update of taking the content from this memory and writing it to T1 is only available in the write back stage, whereas the second instruction, the register T1 value is already obtained from the register in the decode stage. Okay, so if we do not handle this, then when we read the register T1 we are going to be getting the wrong value, okay, because it's not the updated value from instruction 1. Okay, so this is just an example of a hazard, and we are going to be examining the different hazards that this sequence of instructions has, and how different mechanisms in the processor is going to help us. So let's look at the part A. So in part A, we are given in the question that we have no mechanism to handle raw data hazards as well as control hazards, and we have to stall on these hazards until they disappear. Okay, so let's examine the sequence. So the first instruction, okay, will go and start, okay, and we know that for the second instruction, this T1, okay, is needed, okay, and this T1 in the first instruction is only updated in the write back stage. So only when the write back stage is completed, okay, I can go past the decode stage. Okay, so always remember that when I read a register, I'm reading it in the decode stage, okay, and if it does not hold the correct value, then I need to stall until it gets updated. Okay, so this write back and decode can both happen together in the same clock cycle, because in one clock cycle, okay, the writing to the register, okay, is done in the first half and the reading is done in the second half. Okay, so in that same clock cycle, cycle 5, the first load word instruction would be updating register T1, and in the second half of the clock cycle I will be able to read out the correct T1 value from the register file. Okay, so that is why instruction 2 must stall in the decode stage until the write back of the first instruction is complete. Okay, and since the second instruction is already stalled at the decode stage, the first instruction has to be stalled in the fetch stage. Sorry, the third instruction has to be stalled in the fetch stage. Okay, so every stage can only have one instruction at a time. Okay, so if the second instruction is stalled at the decode stage, the third instruction has to be stalled at the fetch stage. Okay, and so when the second instruction eventually gets past the stall and goes on to the execute stage, okay, it carries on, but we can see that the third instruction, I3, needs the updated T1 to be stored to a memory location. So this T1, okay, needs to be updated from the instruction 2. So again, we are having a similar issue. The second instruction, I2, will update T1 only in the write back stage. So only when the write back stage is complete for I2, the third instruction, I3, can go past the decode stage. Okay, so in cycle 8, okay, we will have a similar thing happening here, where in the first half of the clock cycle, the I2, instruction 2, will update T1, and in the second half of the clock cycle, I will be reading the updated T1. Okay, and going on to, okay, after that, of course, I3 carries on execution once it goes past the decode stage. Going on to instruction 4, okay, instruction 4 and instruction 3, both of them use T2. Okay, but there is no dependency in this case, because here I'm doing a read from T2, here also I'm doing a read from T2. Okay, so there is no dependency, but since the I3 was stored in the decode stage, I4 is stored at the fetch stage. Okay, so only at this point of time, clock 8, when I3 moves out of the decode stage to the execute stage, I4 can move from the fetch state to the decode stage. Okay, and I4 can carry on without any issues after that. And when we come to I5, we can see that I5 has a dependency on T2. Okay, we need the updated value of T2, but we know that the T2 is only going to be updated in the write back stage of I4. Okay, so again, when the I4 hits the write back stage, I'm going to do the same thing, which is the update of the T2 register, and in the same clock cycle, I5 will be able to read the updated value of the T2 register. Okay, and then we can go past the decode stage in I5, and then we carry on execution. And since I5 was stalled in the decode stage, okay, I6 has to be stalled in the fetch stage. Okay, and after I go past the fetch stage, okay, you can see that I again have a similar issue where I am checking, the branch instruction is checking for T4 with register 0, but T4 is again only updated in the write back stage of I5. So again, I'm having the same scenario over here. Okay, so the write back stage of I5, okay, will complete in cycle 15, and in the same cycle, the instruction 6 can do the decode. And once that is done, I will be able to carry on. Okay, and since this is a we do not have any mechanism to handle hazards of control as well as data, I need to wait until the MEM stage is completed. Okay, once the MEM stage is completed, that is where I am able to know the final decision on the branch. So in the next clock cycle, cycle 18, I will be able to move over to the correct instruction. Okay. Okay, so that is the uh, whole timing sequence. Okay, so in terms of number of clock cycles, we can see that I take a total of 17 clock cycles here to complete one iteration. Okay, why 17 and not 18? Because in 18 I complete the last instruction, but it also overlaps with the start of a new iteration of the loop. Okay, so if you analyze the code and based on the information given, we know that the loop is running for 100 iterations. So it is total of 18 minus 1, okay, multiplied by 100 iterations, okay, plus 1. Okay, this plus 1 is because for the last time that I run the loop, I need this one more clock cycle here for the write back. Okay, so this will give me 1701 clock cycles. Okay, so let me repeat the last part again. Though you see it takes 18 clock cycles to complete this entire sequence, this 18 is inclusive of the overlap of the next iteration of the loop. Okay, so because it is looping for 100 times, okay, and there is one overlap for each loop, okay, we can remove that for the number of times we do the loop. So we only need to calculate for 17 clock cycles for 100 iterations of the loop. Okay, but we need to add back this last clock cycle for that final iteration of the loop when we don't need to branch back. Okay, so that gives us a total of 1701 clock cycles to complete this sequence of instructions on a pipeline processor that does not have any form of data hazard or control hazard mechanism. Okay, so I hope uh, it is clear on what is actually happening when we are and why we need to stall the processor. So always remember, we are stalling the processor in a particular stage because we need to wait for the correct data to be updated in the pipeline register in the register file before we can move on to the next stage and so on. Okay, so that is the reason why we are stalling the processor. Okay, so that is for part A. Now let's look at part B. Okay, for part B, we are given that the processor has full forwarding paths, okay, for raw data hazards. Okay, but control is still handled by stalling the processor. Okay, control is still handled by stalling the processor. So how do we go about doing this? Okay, so if you look at the first instruction, if the first instruction is updating a register and we need that register for the second instruction, okay, as one of its source, okay, if the first instruction is a load word, then you have no choice but to have at least one stall. Okay, why? Because a load word instruction, the data is only available after I complete the mem cycle. Okay, after I read the data from the memory, then only it is available to me. Okay, so I have to wait until the mem cycle is completed before I can use it in the second instruction. Okay, so I have to have at least one stall before the second instruction can go on to the exe stage. Okay, so that is why the second instruction here, even though I'm doing forwarding, I'm forwarding from the mem to the exe stage. Okay, from the mem to the exe stage here. Okay, so of course it is interesting to note that I stall in the decode stage. Okay, but when I go past the decode stage, of course I read T1 value. So at this point of time, I actually do read T1 value. Okay, but the T1 value that I read here is the wrong T1 value. Okay, because the correct value is the one that is actually from the memory that I'm forwarding. Okay, how do I select the correct one? If you recall our question 2, we have multiplexers at the inputs of the ALU. Okay, so at the ALU side, for both the operands of the ALU, we have multiplexers to select the correct data to be sent through. Okay, so even though I may read the wrong data from the register file, the multiplexer will select the correct data that is coming back from the memory cycle of the earlier instruction. Okay, similarly, okay, once I get the data, I can carry on. And because my second instruction is stored in the decode stage, okay, in cycle 4, my third instruction also has to have a stall in the fetch cycle uh, until the second instruction goes past. Okay, so if I look at the third instruction, again, there is a dependency over here. T1 is updated in the instruction 2 and T1 is needed in instruction 3. Okay, but in this case, this is a normal ALU operation. That means the result of instruction 2, which is T1 plus 1, this result over here is available the moment I complete my exe stage here. Okay, sorry. Okay, so the moment I complete my exe stage here, the T1 plus 1 result is available, which means I can straight away forward it to the exe stage of the subsequent instruction. Okay, so again, I will be reading the wrong T1, okay, when I come from the decode stage over here, but the multiplexer will be able to select the correct T1 for me and the correct data to be sent through. Okay, so that is your T1 instruction 3. And subsequently, if I look at instruction 4 again has no dependency on instruction 3 because we are doing a read here. Okay, similarly here also we are doing a read. Okay, so there is no dependency, so I4 goes smoothly without any stall, and it does not require any forwarding. But I4 to I5, you can see that the T2 is needed as a source and T2 is updated in instruction 4. So in this case, again, this is a I4 is doing an ALU operation, so the result from the exe stage can be forwarded, okay, to the exe stage of the I5. Okay, and again the same thing happens over here. T4 is updated in I5 and T4 is needed in I6, so I do a forwarding here. Okay, so I can do another forwarding here. Okay, so as long as the forwarding mechanism is in place, you can see that I do not need to wait for the write back stage to be completed, because I can straight away take the ALU output of the previous instruction and bring it back as the ALU input of the current instruction. The only exception to this is, like I said, okay, when I have a load word instruction, okay, when I have a load word instruction and I straight away need to use a register in the subsequent instruction. Okay, that is the only exception, because for load word instruction the data is only available in the memory cycle. Okay, so when I6 is executing, okay, for part B we are told that there are no mechanisms to handle control hazards. Okay, so I need to wait until the mem stage is complete, then only I will know the correct branch address. Okay, so subsequently after the mem stage is complete, I can go ahead and branch to the correct instruction and start. Okay, so in terms of timing, as you can see, even though I take 11 clock cycles to complete the last clock cycle, there is an overlap here. Okay, because I'm fetching the new instruction, so I only have to count until 10. Okay, so it is 11 minus 1, okay, multiply by 100 for the number of times of the loop, plus 1. Okay, again this 1 is because in the last iteration of the loop I do not have an overlap, so I need to include this one. So this will give me 1001. Okay, so 1001 clock cycles for this part B in the pipeline processor analysis. So again, in part B, we are having full forwarding for raw data hazards, but we do not have any mechanism to handle control dependency. Okay, so that is the result that we get. Okay, so let's go on to part C. Okay, so part C, what are we having? We are having full forwarding again for raw data hazards. Okay, and we are having early resolution in ID stage. Okay, so early resolution basically has additional hardware in the decode stage to make a decision on whether the branch is to be taken or not. Okay, so let's do analysis here. So the first part is actually exactly the same, okay, as the part B, okay, because since we have full forwarding part, okay, so there is a stall over here at the mem stage, okay, but from here I'll forward here to the exe stage, so the T1 gets forwarded here, okay, after I read from the memory. And because of a stall in I2 in the decode stage, my I3 will also have to stall in the F stage. Okay, subsequently the T1 here will be forwarded here, so there will be a forwarding over here. Okay, for I3 to I4 there is no dependency, so you don't need to worry. And here to here there is a forwarding. Okay, so I4 to I5 there's a forwarding, and again here to here there's a forwarding. Okay, um, so this is where the early resolution plays a part. Okay, with early resolution, okay, we know that we can make the decision in the decode stage. Okay, but what is happening here is you can see that the branch instruction is checking for T4, and T4 is only updated by I5. Okay, over here. Okay, which means that this operation, subtraction operation of T3 and T2, the result is only available in the uh, exe stage, okay, of the I5. So only when the exe stage of I5 is complete, I can use that data to do a resolution in the decode stage of the I6. Okay, so again, rightfully, if instead of it being T4, okay, if it was T5, that means okay, so for example, if it was a BNE and T5, okay, with 0 and loop, okay, then T5 has no dependency on the earlier equation, so in that case we would not have had to do this stall over here. Okay, so the only reason why we have a stall over here is because of the fact that um, we are checking for T4 and T4 is updated in I5. Okay, so once we make a early resolution in the decode stage, the next clock cycle itself, we can jump to the correct instruction and start to execute. Okay, so now that we have this, we can see that in terms of timing analysis, even though we take 12 clock cycles to complete everything, there is three uh, stages of overlap. Okay, so the last three clock cycles of I6 actually overlap with the new iteration of the loop. Okay, so in terms of analysis, we can say it is 12 minus 3, again multiply by 100 iterations of the loop, plus 3. In this case, why plus 3? Because in the last iteration of the loop, we need to add in the 3 clock cycles, so that gives us 903 cycles to complete this entire iteration of this code here. Okay, so I hope this is clear. So part C and part B are actually very similar in the first part of the analysis. Only thing is we have the early resolution in instruction 6, okay, which changes the behavior. Okay, so let's go on to part D. And in part D, what do we have? Okay, so in part D, we are told that we are having branch by branch prediction using the predict taken scheme. That means we always say that the branch is going to be taken. Okay. Early branching is not implemented and we still resolve it in the MEM stage. Okay, so how do we go about doing this? Okay, so if we look at the analysis, the first part is again going to be exactly the same. Okay, the reason why it's exactly the same is because we still have all the forwarding mechanisms for data. Okay, so this will always happen. Okay, and this um, second instruction, stall here and stall here, is because we are having a load word instruction over here. Okay, and subsequently, okay, again I'm going to quickly just run through here. So here there is a forwarding. Okay, instruction 4, there is no forwarding involved, but here 4 to 5 there is a forwarding. Okay, and then 5 to 6. Okay, so from the 5 to 6, again I need here T4 T4, so from here to here I can do another forwarding. And finally in this case we are saying that in part D we are saying that we are always going to take the branch. Okay, that means with the predict branch taken, I will always carry on to fetch the instruction based on the address given by the branch target address. Okay, so this will always be the branch target address because I'm saying that the branch is always taken. Okay, so I'm always going to go back to the loop. Okay, so the loop here is missing, so this is the loop. Okay, so if I look at the analysis, okay, basically it takes 11 clock cycles. Okay, but as we know, the 4 clock cycles have overlap here, so it is basically 11 minus 4 multiplied by 100, okay, plus 4 for the last iteration of the loop, which is 704. Okay, so you can see that this is giving us a very good performance in terms of number of clock cycles. Okay, because we have full raw data hazard handling. Okay, and we are using a branch prediction scheme that predicts the correct response for all the time except for the last iteration where we do not take the branch. Okay, so this is giving us a good performance. Now in the last part, part E, we are saying that the branch is handled by the delayed branching, which is similar to part B. Okay, that means there is no early detection. Okay, and if we look at the analysis, this is exactly the same as what we saw for part B. Okay, it's exactly the same as part B. Okay, so instead of having any early detection or branch prediction, what we are doing is we're having three stalls. Okay, so the three stalls are actually the three NOP over here. Okay, so the three NOP is basically there because we are only able to make a decision on the branch when it reaches the MEM stage. Okay, so once it reaches the MEM stage, then in the next clock cycle, I'll be able to fetch from the correct address. Okay, so in this kind of situation, what can we do is we can try to uh, reorder the code in a way or modify the code such that we can make better use of these three clock cycles here. Okay, so this code here, okay, shows us one way in which we can do it. Okay, so if I look at the code, what am I doing? I'm saying that the first instruction is a load word instruction, which is the same as over here. And then what I've done is I've moved I4 over here. Okay, the reason why I4 has moved here is because if I have an instruction that is going to use T1, okay, in the second instruction, we know that there's always going to be a, uh, a delay, okay, because I need to wait for the MEM cycle to complete before I can move forward. Okay, so to avoid that delay, okay, I'm going to put in an instruction that has no dependency on T1. Okay, so this instruction I4 has no dependency on T1, so I'm going to put it here. And subsequently, I go on to I5. Okay, so I5 comes here. And then I do a branch instruction here. Okay, when I do a branch instruction over here, okay, since we are not doing any form of early detection, okay, and what am I going to do here is I'm actually going to have three delay slots here, correct? So this is delay slot 1, and this delay slot 2, and this delay slot 3. Okay, so these three delay slots, okay, instead of uh, having a NOP, I'm actually putting instructions now. And these instructions are the instructions that were earlier in the instruction 2 and the instruction 3. Okay, so you can see that if I were to go through the code, logically I am not making any changes, okay, but the code has changed slightly in a sense that in the instruction 3 previously I used offset of 0, here I use offset of -4, and the only reason is because I already do the addition over here. Okay, so I did the addition earlier, so when I'm doing the store word over here, I do a offset of -4. Okay, so you can see that this is one way in which you can reorder code as well as slightly modify the code, okay, to make better use of the delay slot. Okay, so the reason is the delay slots are going to be there the moment the branch is executed. Okay, and if you have no other mechanism such as early detection or branch prediction, the three delay slots will be considered a wastage of clock cycles. So what we can do is we can put in useful instructions in the delay slots that do not affect your logic in any way. Okay, so again, this may not be so straightforward. You need to have some thinking as to what I can put in the delay slot and how I can reorder instructions without affecting the output or affecting the logic of the code. Okay, so with this, if I look at the timing analysis, I'll get something like this. Okay, so you can see that because right now the first instruction is loading to T1, but the second instruction has no dependency, and the third instruction also has no dependency, okay, on the T1, there is actually no need for me to have any form of forwarding, okay, from I1 to I4, okay, and from I4 to I5, I still have the forwarding over here, okay, so I4 to I5, I still have the forwarding, okay, but you can see right now from instruction 1, first instruction to the second instruction, there is no longer a need for me to stall the processor as we saw from the earlier examples. Okay, so this is one example, okay, where we can actually reorder code, okay, and change the dynamics of the pipeline processor. okay, by intelligently making use of the delay slots. Okay, so the three delay slots, okay, we still have one NOP, okay, but the earlier two delay slots are now you doing useful instructions, which are actually part of what we want to execute. Okay, so I hope that this video has given you a quick and a good overview of the whole sequence of analysis for pipeline processes. Okay, so hope that this helps you with your understanding. Okay, so thank you.